Hello, and welcome to Psychology for Sleep. If you're listening to this, chances are you're somewhere quiet. The lights are low. The world outside your window is settling into a hush. Maybe you can see a sliver of the night sky, a deep, dark canvas pricked with the faint, steady light of stars. It's from this place of stillness that we begin our journey tonight. Not with a roar, but with a question. A simple one, really. One that might have crossed your mind on a night like this, looking up, how far can we go? Not in our dreams, not in the distant future, but right now. With the metals and engines and courage we possess today, what is the absolute limit of our reach? Where is the edge of the map, the point beyond which we cannot step? The answer, as it turns out, begins not with a rocket on a launch pad, but with something much closer to home. It begins with the very air we breathe, and the invisible force that holds us to this world. It begins with understanding the cradle we live in and what it truly takes to leave it. So, let's start here. In this room, feel the weight of your body against the bed. That weight, that comforting, constant pressure, is our first and most fundamental boundary. It's gravity, the same force that makes rivers flow and keeps the moon circling us. It's what holds our atmosphere in place, a thin, fragile blanket of gas that shields us from the cold and the radiation of space. For nearly all of human history, this was the ceiling of our world. The sky was a dome we could only look at, never touch. The first people who dreamed of flight imagined feathers and wings, not rockets. Their gaze was on the air itself. We were creatures of the soil and the sea, able to explore only what gravity allowed, and that gravity is both our protection and our prison. It's the reason leaving this planet is so profoundly, fundamentally hard. To travel anywhere in the universe, we first have to fight against the very thing that keeps us alive. We have to break the bond that has held all of life, for all of time, to this single spinning rock. The edge of our journey isn't out there among the stars. Not yet. It's only 100 kilometers straight up, a distance you could drive in an hour. But vertically, it's a journey through everything that sustains us into a place that cannot. This is the story of that first hardest step, the step out of the cradle, main body. I want you to picture that line. Not a wall, not a fence, but a transition. About 100 kilometers above the sea, the air becomes so thin that it can no longer support flight. Airplanes with their wings that push against the air can no longer generate lift. Their world ends and ours, the realm of space, begins. This invisible boundary is called the Kármán line. It's the point where the sky fades into black. It's where flight ends and orbit begins. To reach it, a rocket must claw its way up through the thickest part of our atmosphere, a brutal, fiery climb. But here's the secret. Getting up there isn't the hard part. The hard part is going fast enough to stay there. You see, orbit isn't about height. It's about speed. Imagine throwing a ball. It flies in an arc and hits the ground. Now, imagine you could throw it so incredibly fast that as it falls, the curve of the earth falls away, beneath it, at the same rate. It keeps falling, but it never hits the ground. It's in a perpetual state of free fall. That is orbit. To achieve that around Earth, you have to be moving sideways at a staggering 28,000 kilometers per hour. That's about 7.8 kilometers every single second. You have to be moving so fast that you outrun the planet's pull. This was the first great human victory over gravity. It wasn't about escaping it entirely, but about learning to dance with it. On April 12, 1961, a Soviet cosmonaut named Yuri Gagarin became the first person to do this. His spacecraft, Vostok 1, was a tiny pressurized sphere. He circled the Earth just once, a journey that lasted less than 2 hours. He only traveled a few hundred kilometers above the surface, a trivial distance on a cosmic scale. But that small leap was the first time a human being truly left the cradle of the atmosphere. He was the first to look down, not up, at our world. Since then, we've built a steady routine of reaching this edge. Satellites circle overhead by the thousands. The International Space Station glides along at about 400 kilometers high, a permanent outpost where people live and work for months at a time. To an astronaut aboard the station, Earth is a living map unfurling beneath them. Cities flicker like clusters of stars at night. Storms swirl in vast, graceful spirals. A sunrise arrives every 90 minutes, a blinding flash of light that splits the darkness every hour and a half. It sounds impossibly far away, doesn't it? A place where people float weightless, watching our world from a divine perspective, but in the scale of the solar system, it's barely a whisper away. Let me give you a sense of that scale. If Earth were a globe just 1 meter across, the space station would be orbiting less than a centimeter above its surface. That's it. All of human spaceflight, all our orbiting laboratories and telescopes and satellites exist in a layer thinner than the varnish on that globe. We are not spacefarers yet. Not really. We are clingers. We cling tightly to our planet, living and working just beyond the air we breathe. We have mastered the art of falling around the Earth without hitting it. But to go farther, to truly travel beyond this gravitational embrace, requires something else. It requires not just speed, but escape. There is a number, a velocity, that represents true freedom from Earth. It's called escape velocity, and it is about 11.2 kilometers per second. That's over 40,000 kilometers per hour. Reaching that speed requires an explosion of energy so immense that it consumes almost the entire mass of a giant rocket. Think about that for a moment. A Saturn V rocket, the kind that took people to the moon, stood taller than a 30-story building. Most of that colossal structure was just fuel and tanks, giant cylinders of liquid oxygen and kerosene, all burning away in a few furious minutes, just to push a small, cone-shaped command module the size of a car to the speed necessary to break free. It's a brutal, inefficient, and terrifyingly beautiful process. It's the sound of freedom from our cradle, a freedom paid for in fire and thunder. And this leads us to the central frustrating problem of distance in space travel, a problem that defines our reach. It's called the tyranny of the rocket equation. In simple terms, it means that for every extra bit of speed you want, you need exponentially more fuel. But that fuel itself has mass, which means you need even more fuel to lift that fuel. It's a vicious, constraining loop. It's the reason our reach is so limited. It's the chain that keeps us tied close to home. Every journey we dream of, to Mars, to the asteroids, to the stars, is a negotiation with this cruel equation. To go faster, we need to be lighter. To be lighter, we have to give something up. More speed, more fuel, more weight. It's a puzzle that has haunted engineers for a century. So, we find clever ways to cheat. We don't just blast straight out into the solar system. We spiral upwards slowly, using the gravity of the Earth, the Moon, even other planets, like a slingshot to give us a free boost. We build ships in orbit piece by piece. We design engines that are less like violent explosions and more like a gentle, continuous push, engines that can run for months or years, patiently building up speed. We are learning to be patient because the universe demands it. Right now, as you lie here in the quiet, there are people living just on the other side of that thin blue line. They are floating in a metal can, looking down at all of us. They are the current guardians of the edge. Their presence there is a miracle of cooperation and engineering. It is proof that we can leave, but it is also a reminder of how close we still are. From their vantage point, the Earth is everything. It is life and home and safety. The blackness that surrounds it is infinite and empty. To go out there, into that emptiness, is to leave behind the only safety net we have ever known. We have learned to reach orbit. We have learned to live there for a time. We have even briefly learned to leave it. But the question that hangs in the silence, the question that follows every sunset they witness from above, is the same one we started with. We've learned to climb out of the cradle, but how far can we walk? The silence of space is not like the quiet of this room. It is absolute. No wind, no sound, no whisper of air. Just the cold and the distant, unwavering light of stars that have burned for billions of years. From orbit, our world looks peaceful, unified, a single beautiful whole. The boundaries and conflicts that fill our lives vanish from that distance. There is only one home, one fragile sphere of life, hanging in the void. We reached that perspective in a few short decades. We went from gunpowder rockets to lunar landings in a lifetime. The generation that first saw the curve of the Earth from space is still with us. Their courage, their precision, their willingness to sit on top of those towers of fuel gave us the first look back at ourselves. They crossed the first and hardest frontier. They proved that we could leave, but as their spacecraft circled the planet, a new question must have formed in their minds. A question that we have been trying to answer ever since. We made it to the edge, but what lies beyond? I hope the quiet is still with you, that the day has fully receded, and the night feels like a blanket insulating you from the world. In our last chapter, we stood at the edge of the cradle. We looked up at that invisible line, the Kármán line, where the sky gives way to the void. We learned that getting there isn't about height, but about speed, a furious, sideways velocity that lets you fall around the Earth forever. We ended with a question. We had reached the edge, but what lies beyond? Tonight we will answer that, but not in the way you might expect. Because the first thing that lies beyond the cradle isn't grandeur or wonder or even answers. It's noise. It's violence. It is a sheer explosive wall of force that must be conquered just to take that first trembling step. The story of how we cross that threshold isn't a clean scientific diagram. It is a story of fire and fear, of mathematics and madness, of fragile machines and the few people brave enough to ride them. It's the story of the first steps into the abyss, steps taken not with confidence, but with a courage that was, I believe, quieter and more profound than any we have known since. So let's leave the quiet of this room. Let's travel back to a time when the sky was not a highway, but a wall. A time when to even speak of leaving Earth was to invite ridicule, or worse, to be called a fool. The journey beyond begins not with a hero's shout, but with the tentative scratch of a pencil on paper in a room far away from any launch pad. Hook. Before there were rockets, there were equations. Before there were astronauts, there were dreamers in small rooms, surrounded by books, trying to solve the problem of the sky with nothing but the laws of physics and the power of their own imagination. One of these dreamers was a man named Konstantin Tsiolkovsky. In the late 19th and early 20th century, in rural Russia, he worked as a schoolteacher, largely self-educated and almost completely deaf. He never built a rocket that flew. He never even saw one. But in his mind, he saw everything. He calculated the mathematics of escape velocity. He designed on paper multi-stage rockets and orbital stations and sealed cabins for life support. He understood that chemical propulsion was the key, that to break free you had to expel mass backward to move forward. He once wrote a sentence that would echo through the following century, a sentence that is the very soul of our journey. He said, "The earth is the cradle of humanity, but one cannot remain in the cradle forever." It was a prophecy, a quiet, patient one. He knew he would never see his ideas take flight. He was building a ladder he would never climb, for a generation he would never meet, and, while he was writing, others were starting to build. In America, a physicist named Robert Goddard took those theories and began to give them shape. He started small in a vacant field in Massachusetts, with rockets no bigger than a person's arm. They were clumsy, sputtering things. They often exploded on the launch stand or veered wildly off course. His neighbors thought he was a nuisance. The press ridiculed him, but with each failure he learned. He patented the first liquid-fueled rocket, understanding that liquid propellants could be controlled, could be throttled, could offer the sustained thrust needed for a real journey. He was a quiet, meticulous man, and he worked in near-total isolation. He wasn't trying to conquer space. He was just trying to solve an engineering problem, one failure at a time. He once launched a small rocket that went about 40 feet into the air. To anyone else, it was a pathetic sight. To him, it was a universe of possibility. Meanwhile, in Germany, the ideas were taking a darker, more urgent form. A society of enthusiasts, the VFR, or Society for Space Travel, was experimenting with their own rockets. Among them were young, brilliant minds like Wernher von Braun. They were captivated by the dream of spaceflight, but their work would soon be co-opted by a regime that saw not a gateway to the stars, but a pathway to destruction. This is the uncomfortable, tangled truth of our first steps. The technology that would eventually carry us to the moon was born not from a desire for exploration, but from the furnace of war. The first human-made object to ever touch the edge of space was not a vessel of peace. It was a weapon, the V-2 missile. It was a terrifying creation. 14 meters tall, fueled by liquid ethanol and water, it could arc 80 kilometers high and come screaming down on its targets at supersonic speeds, with no warning, no defense. It was built by forced labor under horrific conditions. Its purpose was terror, and yet it proved something monumental. It proved that a rocket could climb past the thin blue line. It proved that we had the power, however misapplied, to touch the void. When World War II ended, the race for this technology wasn't about science. It was a frantic scavenger hunt. American and Soviet forces raced to capture the remaining V-2s, the manufacturing plans, and most importantly, the scientists who had built them. The dream of Tsiolkovsky and the experiments of Goddard were now the spoils of war. The cradle was about to be left behind, not in a spirit of collaboration, but in a fierce, silent competition between two superpowers that distrusted each other completely. The sky was no longer a frontier. It was a battlefield, and so the stage was set. The equations were written. The engines were tested. The political will, forged in fear and rivalry, was there. All that was missing was the signal to begin, the signal that would tell the world that the cradle was now officially open. That signal didn't come as a speech or a declaration. It came as a sound, a simple, steady, mechanical beep emanating from the heavens. Main body. It was October 4th, 1957, and on that day, the Soviet Union changed the world forever. They launched a small, polished metal sphere no bigger than a beach ball with 4 long antennae whiskering out from its sides. They called it Sputnik 1. It weighed just 83 kilograms. It did almost nothing. It had no cameras, no sophisticated instruments. Its only function was to transmit a constant, steady beep, beep, beep on a radio frequency that amateur operators around the world could easily pick up. But what it did was everything. It was the first artificial satellite, the first human-made object to achieve orbit. The first thing to escape our world and circle it freely. You have to understand the shock of this moment. For most people, space was still the realm of fantasy. And then, one night, you could go outside, look up, and see a tiny moving star drifting silently from one horizon to the other. And you knew, with chilling certainty, that it was not natural. It was ours. Something built by human hands was now up there, looking down on us. That steady, emotionless beep was the sound of the old world ending and a new, uncertain one beginning. It was a sound that stripped away any sense of security. If the Soviets could put a satellite in orbit, what else could they put up there? The sky, for the first time in human history, felt like a place of threat. The United States was caught completely off guard. The public was terrified, then fascinated, then inspired. The space race had begun, not with a bang, but with a beep. Just a month later, the Soviets struck again. Sputnik 2 was launched. And this time, it carried a passenger. A small mixed-breed dog named Laika. She was a stray, plucked from the streets of Moscow. She was gentle and tolerant, and she was about to become the most famous dog in history. Her mission was one way. The technology for a safe re-entry hadn't been developed yet. The scientists knew she would not survive. They gave her a special gel for food and hooked her up to sensors to monitor her heartbeat, her breathing. When the rocket lifted off, The data showed her pulse tripled from the stress and vibration. But once she reached weightlessness, it settled down. For a few hours, Lika floated in her tiny pressurized cabin, the first living creature to orbit our planet. She proved that a mammal could, at least for a short time, withstand the violence of launch and the strange sensation of zero-G. Then, as planned, her life ended. It was a tragedy, but it was also a data point. A cold, hard, necessary one. Her sacrifice pushed our understanding forward. It showed us that the greatest barrier might not be engineering, but biology. Could life truly endure out there? America scrambled to respond. In early 1958, they launched Explorer 1, built by a team led by the German-born scientist Wernher von Braun. It was a success, and it made the first major scientific discovery of the space age, the Van Allen radiation belts, vast zones of charged particles trapped by Earth's magnetic field. This was a crucial finding. Space was not an empty, benign void. It was an environment filled with invisible, deadly hazards. Future travelers would have to navigate through these zones of radiation or find a way to avoid them. The race was now on in earnest, and it quickly moved from machines to men. The next logical, terrifying step was to put a human being inside one of those capsules. The Soviets again moved first. They created the Vostok program. The spacecraft was a sphere, barely large enough for a single person. It had limited controls. The belief was that the passenger would be more of a biological specimen than a pilot, his functions largely automated. They selected a group of Air Force pilots, and from them, they chose a 27-year-old named Yuri Gagarin. On the morning of April 12, 1961, at the Baikonur Cosmodrome, Gagarin was helped into his spacesuit and then into the Vostok capsule. The hatch was sealed. He lay on his back, looking up at the instruments. He later said his heart rate was a calm 64 beats per minute. I don't know if I believe that. I think I would have heard my own heart in my ears. The rocket beneath him was a modified R-7, a giant originally designed to carry a nuclear warhead. Now it was his elevator to the sky. The countdown reached 0. The engines ignited. In his radio transmissions, you can hear him during the ascent. He didn't scream or panic. He simply described what he was experiencing, his voice calm, almost cheerful, with the strain of the G-forces pressing down on him. He said one word over and over as the rocket climbed. "Poyakali," he said. "Let's go." In that moment, he was speaking for all of humanity. The rocket worked. The stages separated. The engines burned as planned, and within minutes, he was there. In orbit, weightless, the first human to ever experience it. He looked out his window. "I see Earth," he reported. "I see the clouds. It's beautiful." "What beauty?" He described the horizon, a delicate bright blue band arcing between the brilliant white of the clouds and the profound blackness of space. He saw the continents, the oceans. He made one single orbit of the planet, a journey that lasted 108 minutes from launch to landing. The return was, if anything, more dangerous than the launch. To re-enter the atmosphere, the spacecraft had to be pointed precisely. A few degrees off, and it would skip off the atmosphere like a stone on a pond, lost forever in space, or it would plunge in at too steep an angle and be incinerated. The heat shield glowed red, then white, as plasma surrounded the capsule, cutting off radio communication for several agonizing minutes. At about 7 kilometers above the ground, the hatch was explosively blown off and Gagarin was ejected, parachuting safely to the Earth in a rural field. A farmer and his daughter were the first to see him, an alien figure in a bright orange suit, descending from the sky. He had done it. A human being had left the planet and returned alive. The cradle was empty. Less than a month later, America sent its own man, Alan Shepard, on a suborbital flight, a much shorter up and down arc. It wasn't an orbit, but it was a statement. We are here. We are competing. Then, in 1962, John Glenn became the first American to orbit the Earth. circling it 3 times in a capsule named Friendship 7. Those early missions were not the sleek, controlled operations we think of today. They were raw, seat-of-the-pants, and incredibly dangerous. The astronauts were test pilots in the truest sense. They were sitting in machines that had only a handful of successful flights behind them. They were putting their lives in the hands of thousands of components, any one of which could fail. The Mercury capsules were tiny, claustrophobic. The astronauts had barely any room to move. They were bolted into a chair surrounded by switches and dials. During launch, the vibration was so intense it made vision blur. The G-forces pressed them into their seats like a giant invisible hand, and then abruptly the engines would cut off. The noise would vanish, and they would be plunged into silence and weightlessness. This was the second great shock after the violence of launch. The sheer, unnerving strangeness of zero-G. Objects floated. A pen let go would hang in midair. Their bodies felt different. Fluids in their bodies shifted upward, giving them puffy faces and stuffy noses. Without gravity to orient them, their inner ears became confused. Which way was up? There was no up. Outside the window was a view that no human language was equipped to describe. The Earth was not a flat map, but a giant curved, living sphere. It had no edges. It was just there, hanging in a blackness so deep it felt solid. The sun, when it rose, did so with a ferocious speed, a sudden, blinding explosion of light that happened 16 times a day. The stars, without an atmosphere to distort them, were not twinkling. They were steady, brilliant, unwavering pinpricks. And the silence. My God, the silence. Not the quiet of a forest or a library, but a total, profound absence of sound. The only noise was the mechanical hum of their own life support, a constant reminder that they were inside a tiny, fragile bubble of habitability, and outside was nothing. These first explorers were not just collecting data. They were collecting perspective. They were the first to see our world as a whole, a single, beautiful, and heartbreakingly isolated planet. The divisions that seemed so important down here, borders, nations, ideologies, vanished from that altitude. There were no lines. There was only one world. And they were the first to feel the true psychological distance of space. They were cut off. The voice from Mission Control was a tinny electronic connection, a thread tying them to home. They were alone in a way no human had ever been alone before. The Gemini program that followed was America's answer to Gagarin's flight. It was the bridge between the simple one-man Mercury missions and the complex 3-man Apollo missions that would aim for the moon. Gemini had 2 seats. Its goals were to prove that we could do more than just survive in orbit. We could work there. We could stay for longer durations. Gemini 5 stayed up for nearly 8 days. We could rendezvous with another spacecraft, a delicate orbital dance essential for reaching the moon, and most dramatically, we could leave the safety of the capsule. The first American spacewalk was performed by Ed White on the Gemini 4 mission. Clad in a bulky spacesuit, he opened the hatch and pushed himself out into the void. He was tethered to the spacecraft by a long umbilical cord that supplied him with oxygen. In his hand, he held a small zip gun, a handheld propulsion unit to maneuver. For 20 minutes, he floated above the Earth, the planet spinning majestically below him. He was a solitary human being, suspended between his tiny ship and infinity. He described it as the most exhilarating experience of his life. But he also learned immediately how unforgiving this environment was. Without gravity or air resistance, every movement had a consequence. A slight push could send him spinning. It took immense effort and fuel to stabilize himself. It was beautiful, but it was also a stark lesson in vulnerability. Outside that metal shell, a human body would last about 15 seconds before the blood in their veins began to boil from the lack of pressure. The suit was all that stood between him and instant death. The Gemini missions were a brutal, relentless training ground. They practiced docking over and over. They battled malfunctioning thrusters, faulty computers, and the ever-present specter of fatigue. They were proving that humans could be more than just cargo. They could be pilots, engineers, and problem solvers in this new, alien realm, and through it all they were learning the hardest lesson of spaceflight: how to come home. Re-entry is, in many ways more terrifying than launch. You are coming back from a place of serene weightlessness and silence into a maelstrom of fire and force. The spacecraft must hit the atmosphere at exactly the right angle. Too shallow, and you skip off into space. Too steep, and the G-forces become unbearable, and the heat incinerates you. As the capsule plunges into the upper atmosphere, the friction of the air, compressed at hypersonic speeds, creates temperatures hotter than the surface of the sun, up to 3,000 degrees Celsius. The heat shield, a specially designed ablative material, doesn't just resist the heat. It sacrificially burns away, carrying the intense thermal energy with it in a cloud of vaporized material. From the ground, a returning spacecraft looks like a meteor, a brilliant streak of light tearing across the sky. Inside, the astronauts are pressed back into their seats as deceleration forces climb to several Gs. The plasma sheath surrounding the capsule blocks all radio communication, a period known as the communications blackout. For several minutes, Mission Control has no idea if the crew is alive or dead. They can only wait and hope that the physics holds. Then, if all goes well, the plasma fades, the radio crackles back to life, and the spacecraft slows to a point where parachutes can be deployed. The final descent is a slow, swinging drift down to the ocean or the land. The moment the capsule hits the water, the mission is over. The adventure becomes memory. The astronauts are back. They are on the only planet they know how to live on. But they are changed. They have seen the world without borders. They have felt the emptiness. They have been somewhere that no human body was ever meant to go, and they have returned because of precision, cooperation, and an unshakable trust in the systems that supported them. These first steps were not graceful. They were clumsy, explosive, and fraught with risk. But they worked. They proved that travel beyond Earth wasn't science fiction anymore. It was a process we could repeat, improve, and build upon. We had learned to launch, to orbit, to work, and to return. We had crossed the abyss, not with a single leap, but with a series of terrifying, triumphant stumbles. The sky had been pierced. The planet had been circled. We were no longer just earthbound creatures, but a new question was already forming, a question born from the view of a small blue marble hanging in the blackness, a question that would demand an even greater leap into an even deeper darkness we had learned to leave. I hope you're settled in, that the day has fully released its grip and the night feels like a wide, open space. In our last chapter, we lived through the fire and thunder of the first steps into the abyss. We felt the vibration of those early rockets and the profound silence that followed. We stood with Gagarin, Glenn, and White as they became the first of our kind to touch the void, to work in it, and to return forever changed. We ended with a question born from that hard-won experience. We had proven we could reach space. We had even proven we could survive there for short, frantic missions. But survival is not the same as living. A brief visit is not the same as setting up a home, and that is our next step. The most logical, and in many ways the most audacious step we have ever taken. We didn't just want to visit the abyss. We decided to build a house in it, a place to live, to work, to sleep, and to dream, in an environment that offers no air, no water, no ground, and no natural shelter. Tonight, we leave behind the daring single-shot missions of the past. We move from the age of explorers to the age of settlers. We are going to move in. We are going to learn what it truly means to make a home in a place that was never meant for life. So, let's push off from the edge of the cradle, not for a quick visit, but for an extended stay. Let's float through the hatch of humanity's first true house in space, and learn what it takes to live in a world without up or down, where the sun rises and sets 16 times a day, and where the only thing separating you from infinity is a metal shell thinner than the skin of an airplane. The International Space Station is, without exaggeration, the most complex and expensive structure ever built by humanity. It's a collection of modules and solar arrays, a sprawling interconnected maze of laboratories and living quarters that stretches the length of an American football field. It weighs over 400 tons. It travels at 28,000 kilometers per hour. and it has been continuously inhabited by human beings for over 20 years. We see pictures of it, gliding serenely against the backdrop of Earth, and it can seem almost ordinary. We hear about astronauts floating through its modules, conducting experiments, and it feels like a routine, a fact of life. But I want you to forget that for a moment. I want you to imagine the sheer, terrifying improbability of it. You are about to move into a house that is falling. It is falling around the Earth at just the right speed to keep missing it. Every single system that keeps you alive, every breath of air, every sip of water, every morsel of food, every degree of temperature must be manufactured, recycled, or imported from a world that is, at its closest, 400 kilometers away. There is no backup planet. There is no stepping outside for fresh air, a single small puncture in the wall, a failure of a pump, a fire. Any of these would be a catastrophe that unfolds in minutes. With no possibility of escape, this is not a comfortable home. It is a fortress of habitability, a masterpiece of engineering built on a knife's edge. The people who live there are not just scientists. They are caretakers, mechanics, and gardeners in a sealed, artificial biosphere that is perpetually on the verge of breaking down. They are the first of our kind to learn the rhythms of a life untethered from Earth. They are learning the daily, mundane, and extraordinary realities of what it means to be a spacefaring species. And the lessons they are learning there, the quiet, unglamorous struggles of daily life in orbit, are the very foundation for every journey we will ever make beyond. To understand how far we can travel, we must first understand how to live away from home. We must understand the economics of air, the politics of water, and the psychology of a view that never stops moving. The story of the space station is the story of us learning to build a campfire in the cosmic wilderness. It is the story of how we learn to stay. The idea of a space station didn't appear suddenly. It was the natural, almost inevitable next step. As soon as we knew a human could survive in orbit for a few hours, we began to dream of staying for days. As we managed days, we dreamed of weeks. The cramped utilitarian capsules of the Mercury and Gemini programs were like tiny, exposed lifeboats. For spaceflight to become sustainable, we needed more than a lifeboat. We needed an ark. The first tentative attempts were stark and sobering. The Soviet Union led the way again with the Salyut program in the 1970s. These were simple, cylindrical stations, little more than enlarged rocket stages, with a door on one end. They were austere and basic. In 1971, the crew of Soyuz 11 spent 23 days aboard Salyut 01, a record-breaking mission that proved extended stays were possible. But their triumph ended in tragedy. During re-entry, a faulty valve caused their capsule to depressurize. Because they were not wearing spacesuits, all 3 cosmonauts were killed. It was a brutal reminder of the station's first hard lesson: the boundary between life and death is a seal, a valve, a breath. The Americans responded with Skylab. Launched in 1973, it was built from the empty third stage of a massive Saturn V moon rocket. It was far roomier than the Salyut stations, with a large open workshop area where astronauts could actually float freely. For the first time, there was a sense of volume, of interior space. 3 different crews lived aboard Skylab for periods of 28, 59, and 84 days. They conducted thousands of experiments, but perhaps their most important discovery was about themselves. They learned what the human body does when you take away gravity. It begins to forget what it's for. Without the constant pull of gravity, the body, a marvel of evolutionary adaptation to Earth, starts to malfunction. Fluids no longer pulled downward shift toward the head. Astronauts develop puffy faces and stuffy noses, their voices sounding congested. The heart, no longer fighting gravity to pump blood upward, weakens slightly. The inner ear, our gyroscope, becomes confused. Which way is up? There is no up. This can cause a debilitating space sickness for the first few days, a nausea of disorientation. But the most insidious changes are slower. Bones, no longer bearing weight, begin to leach calcium into the bloodstream. They can lose up to 1 to 2% of their bone mass every month. Muscles, especially in the legs and back, atrophy from disuse. The body, in its brilliant efficiency, decides that maintaining strong bones and powerful legs is a waste of energy if you're just floating around. To combat this, life on a station becomes a life of forced exercise. Every single day, astronauts are required to spend 2 hours or more strapped to a treadmill or a specialized resistance machine. It's not optional. It's a medical necessity. Without it, they would return to Earth as weak as kittens, their bones brittle, unable to stand. This was the second great lesson of station life. In space, your own body becomes your enemy. Staying healthy is a constant active fight. The Soviet program evolved into Mir, which means peace or world. Launched in 1986, Mir was the first truly long-term orbital home. It was modular, with different sections added over time. It was often described as a scientific laboratory, but those who lived there knew it was closer to a frontier outpost. It was cramped, noisy, and constantly in need of repair. It smelled, by all accounts, like a combination of a machine shop, a gym locker, and a hospital. Life on Mir revealed the third lesson. A home in space is a high-maintenance house. There is a constant hum of machinery, fans, pumps, computers. Silence is a warning sign. It means the systems have stopped. The crew's time is not spent solely on grand experiments. A huge portion of it is dedicated to maintenance. Fixing a broken carbon dioxide scrubber, replacing a faulty pump module, troubleshooting a computer glitch. These are not inconveniences. They are matters of life and death. You become intimately acquainted with every pipe, every wire, every circuit breaker in your home, because your life depends on knowing them. The rhythm of life is artificially imposed to mimic a 24-hour day, to preserve the fragile cycle of the human circadian rhythm. The crew wakes up to an alarm, exercises, works, eats, and has scheduled downtime. But outside the window, the sun rises and sets every 90 minutes. The body's natural clock is constantly being challenged. Sleep can be difficult. Astronauts strap themselves into small sleeping bags attached to the wall. A different kind of bed for every night, if they choose. Then there are the mundane, yet profoundly strange, details of daily life. Eating. Food comes in dehydrated packets or thermostabilized pouches. You inject hot water into a packet to rehydrate mashed potatoes or spaghetti. You have to be careful. A floating glob of ketchup or a cloud of coffee droplets can become a major nuisance, getting into sensitive equipment. Bathing. There are no showers. Water doesn't fall. It forms floating, suffocating blobs. Cleaning involves rinseless shampoos and moist wipes. It's a sponge bath every day for months. The bathroom. This is perhaps the most complex piece of engineering on the station. It uses streams of air, not water, to direct waste into the proper receptacles. It requires precision and practice. As one astronaut famously said, you have to be very, very good at aiming. But amid the routine and the maintenance, there is one thing that never, ever gets old. The view. Every 90 minutes, a sunrise. Not a slow, gentle lightening of the sky, but a sudden, violent blaze of light that erupts from behind the curve of the Earth. The station is flung from utter darkness into brilliant day in a matter of seconds. The windows must have shades, or the sun would fry the interior. And the Earth itself. It is impossible to overstate its effect. It is a living, breathing entity below you. You see the Amazon, a vast green lung. You see the Sahara, a sea of orange and brown. You see the Himalayas, the crumpled backbone of the world dusted with snow. You see the deep, profound blue of the oceans dotted with swirling, brilliant white storms. At night, the planet is not dark. It is alive with light. The continents are outlined in webs of gold and silver, cities, highways, human civilization glowing in the dark. You see auroras, shimmering green curtains of light dancing at the poles. This view changes people. Astronauts call it the overview effect. From that distance, all of human history has happened on that one sphere. There are no borders. There are no flags. There is only one world, breathtakingly beautiful and heartbreakingly fragile. The awareness that that tiny, thin layer of atmosphere is all that protects every known life form in the universe becomes a physical, felt truth. This is the fourth lesson, the psychological one. Living in space gives you a perspective that is both magnificent and humbling. You see everything, but you are utterly separate from it all. This isolation is managed through a constant connection to mission control. There is a continuous stream of data and communication, but it's a delayed electronic connection. You are physically alone with your crewmates in a way that is unprecedented. The psychological strain is real. Crews are carefully selected for compatibility. They must be able to handle stress, boredom, and the intense, inescapable proximity of the same few people for months on end. The International Space Station, the ISS, is the culmination of all these hard-learned lessons. It is a partnership, a symbol that the frontier can bring nations together. Modules built by the United States, Russia, Europe, Japan, and Canada are locked together in orbit. It is a triumph of international cooperation. Life on the ISS is a refinement of life on Mir, but with more advanced technology. The systems are more reliable. Water recycling is more efficient, reclaiming about 90% of the water on board, from sweat, breath, and even urine. The solar panels are vast, turning sunlight into a steady stream of electricity, but the fundamental challenges remain the same. This is not a self-sufficient habitat. It is a parasite on Earth. Every few months, an automated cargo ship, a Russian Progress, an American Cygnus or Dragon, must arrive, bringing food, water, spare parts, and new experiments. These are care packages from home. Without them, the station would die. The waste, the trash, is loaded into these same cargo ships, which are then sent on a destructive re-entry into the atmosphere, burning up over a remote part of the ocean. The station is a magnificent achievement, but it is also a temporary one. Its components are aging. It requires constant vigilance. One day, it will be deorbited, and it will follow its trash into a fiery grave. Its purpose is not to be eternal, but to teach us how to live away from Earth so that we can build the next home and the next. The people aboard the ISS are more than researchers. They are pioneers in a long-term experiment in off-world living. Every system they test, every physiological change they document, every psychological hurdle they clear is a data point for a future mission to Mars or a base on the Moon. They are proving that we can sustain life away from our planet. But they are also proving how hard it is, how costly, and how fragile the balance remains. We have built a home in orbit. We have learned to live in the abyss. But it is a home that is entirely dependent on the world it left behind. We have planted a flag, but we have not yet tilled the soil. We are still living out of cans. We have learned the first, crucial steps of how to stay, but as we look out the window of our orbital home, at the red dot of Mars or the gray disk of the Moon, a new, more challenging question begins to form. If we can barely live 400 kilometers away, how can we ever hope to live millions of kilometers away? The sound inside a space station is the sound of life being manufactured. It is the hum of fans circulating manufactured air. It is the whir of pumps moving recycled water. It is the faint beep of computers monitoring it all. It is not a natural sound. It is the sound of a bubble, a tiny pocket of order we have carved out of a universe of silence and chaos. An astronaut floating at a window can see the entire planet at once. They can see a hurricane forming in the Atlantic and, 45 minutes later, see the lights of Tokyo glittering below. They are connected to everything by sight, but separated from everything by an impossible distance. They are the current guardians of the farthest, most fragile home humanity has ever known. Their daily routine of exercise, maintenance, and science is the quiet, unheroic work of extending human presence just a little farther. Every sunrise they witness is a confirmation that we are still here, that we are still clinging to this tiny island in the void. We have learned to build a house that falls forever. We have learned to recycle our air and water. We have learned to exercise in a world without weight. But for all our progress, we are still tethered. The umbilical cord from Earth has just been lengthened. We have not yet learned to cut it. The station is a classroom, and the lessons are becoming clear. The cost of living in space is constant effort. The price of air is eternal vigilance. We have proven we can live in orbit. But the question that must linger in the minds of those who live there, As they look past the Earth towards the waiting darkness is a question of dependency. He was standing on another world. The powder-fine dust, which they later described as smelling like gunpowder or wet ashes, puffed up around his boots. The gravity was 1/6 of Earth's. Every movement was slow, dreamlike. A simple hop could propel him several feet. The sky above was black, velvety, and filled with stars, even though the sun was blazing down. There was no air to scatter the light, no blue sky. The silence was total, broken only by the sound of his own breathing and the voice from Earth in his headset. Buzz Aldrin joined him shortly after. He described the scene as magnificent desolation. It was beautiful in its stark, alien geometry, but utterly, profoundly empty. They planted a flag stiffened with a wire so it would appear to wave in a world with no wind. They set up experiments. They collected rocks. They took photographs. They were there for only 2.5 hours, but in that short time, they transformed our place in the universe. We were no longer a single world species. Subsequent Apollo missions would stay longer, explore more, and even drive a car, the lunar roving vehicle, across the dusty plains. They brought back hundreds of kilograms of lunar rock, which taught us about the early history of the solar system. They left behind laser reflectors that we still use today to measure the moon's distance with millimeter precision. But the most powerful legacy of Apollo is not scientific. It is philosophical. The astronauts who went there, the 12 men who walked on the lunar surface, all speak of the same thing, the view of Earth. From the moon, Earth is small enough to be blocked by your thumb. It is a vibrant, living blue and white contrast to the dead gray world under their feet. It looked fragile. It looked precious. It looked, as astronaut Jim Lovell of Apollo 8 said, a grand oasis in the big vastness of space. The farthest any human has ever been from Earth was not on the lunar surface, but during the Apollo 13 mission, when they swung around the moon on their free return trajectory after an explosion crippled their spacecraft. They were roughly 400,000 kilometers from home. At that moment, Earth was just a bright star. They were the most isolated human beings in history, their survival hanging by a thread, dependent on the ingenuity of the people on that tiny, distant point of light. The Apollo program ended with Apollo 17 in December 1972. Gene Cernan was the last man to step off the surface. "We leave as we came," he said, "and God willing, as we shall return, with peace and hope for all mankind." Then he climbed the ladder, the hatch was closed, and the ascent stage engine fired, carrying them back to the command module and the long journey home. The footprints, the flags, the abandoned descent stages, the lunar rovers, they were all left behind. The moon was silent once more, and it has remained silent for over 50 years. Why did we stop? The reasons are complex. The political will faded after the moon was won. The cost was immense. The public's attention shifted. We had proven we could do it. The next steps, building a base, going to Mars, were seen as too expensive, too risky. So, the farthest footprints mark a boundary that is both a triumph and a monument to a paused ambition. They are a reminder of what we are capable of when we focus our energy and will. But they are also a question, a challenge. We reached another world. We stood on its surface. We looked back at our own and saw it for what it is. And then we came home, and for half a century, we have not gone back. The footprints are there, unchanged. They are the edge of human travel. They are the proof of our greatest journey. But as we look at them from across the void, a question forms. A question that is perhaps the most important one we can ask about our future in space. If we could go so far, why have we stayed so close for so long? The silence on the moon is different from the silence of orbital space. In orbit, you are still connected. You are falling around the Earth. You see it every 90 minutes. It is your anchor, your context. On the moon, you are truly on another world. The Earth is fixed in the sky or it is absent, hidden behind the lunar horizon. The ground is solid beneath your feet, but it is an alien ground, barren and old. The silence is the silence of geologic time, of eons without weather, without erosion, without life. When the lunar module ascent stage blasted off from the surface, it left behind a profound quiet. The descent stage, a monument to engineering, sits where it landed. The flag, its fabric likely bleached white by decades of unfiltered solar radiation, still stands or has fallen. The footprints remain, perfectly preserved in the fine lunar dust, because there is no wind to erase them. They are a fossil of human ambition. A message we left for ourselves. From our perspective here on Earth, the moon is a constant companion. We see it wax and wane. We see the same face, the man in the moon, looking down on us. But we know now that on that face there are artifacts. There are footprints. There are plaques that say, "We came in peace for all mankind." The Apollo program was a sprint, a burst of almost unbelievable energy and focus. It showed us that we can do the impossible. But a sprint is not a marathon. A visit is not settlement. We reached the farthest shore, planted a flag, and then, for a long, long time, we mostly stayed home. We turned our attention to building a space station in low Earth orbit, learning the lessons of long duration living in space. It was a sensible, practical, and necessary step, but the moon is still there. The footprints are still there. The boundary of human travel is still there, waiting. The question is no longer, can we go? We proved that we can. I hope the stillness is holding, that the world outside your window is a distant, quiet thing. In our last chapter, we moved into the abyss. We learned what it means to build a home in orbit, a fragile island of life perpetually falling around the Earth. We felt the constant hum of machinery, the rigorous daily fight against the body's own decay, and the overwhelming perspective of seeing our entire world, whole and borderless, from a window. We ended with a question of dependency. Our home in the sky, for all its marvels, is still tethered to the world below, reliant on a constant stream of supplies from Earth. We have learned to stay, but we have not yet learned to be self-reliant. Tonight we untether. Tonight we let go of the edge of the pool completely. We are going to venture to the only place beyond our world that has ever felt the weight of a human foot, the only place where our footprints exist untouched by wind or rain. We are going to the moon. This is not a story of building a home. It is a story of a visit, a pilgrimage to our closest celestial neighbor. It is the story of the greatest journey our species has ever undertaken, a journey that remains, even now, half a century later, the absolute boundary of human travel. The footprints are still there, silent and waiting. They mark the edge of our reach, so let's leave the steady orbit of the space station behind. Let's point our ship away from the comforting blue marble and toward the gray, silent world that has watched over humanity since the beginning of time. Let's discover what it took to make those footprints and what their enduring silence means for us today. The distance to the moon is, on a cosmic scale, trivial. It's a mere 384,000 kilometers away on average. A light beam covers that distance in just over a second. We have probes that have traveled billions of kilometers into the darkness, but for a human being, for a creature of flesh and blood, oxygen, and water, it is an almost impossible gulf. It is a distance that requires not just leaving Earth, but truly leaving its embrace. It requires crossing from a realm dominated by our planet's gravity into a neutral point, and then into the gravitational sway of another world. To understand the leap, let's return to our scale model. If the Earth were a globe 1 meter in diameter, the International Space Station would be orbiting less than a centimeter away. The moon on this scale would be 30 meters away, a short walk across a garden. But that walk is across a vacuum so perfect, a silence so absolute, that it has preserved the footprints we left there for 50 years. The Apollo program was born not from a quiet desire for knowledge, but from the fierce urgency of the Cold War. It was a political gambit, a demonstration of technological superiority. Yet, what it produced was something far grander than its origins. It forced human ingenuity to solve the most difficult problem imaginable: how to send life to a world that offers nothing, and bring it back safely. The complexity of that challenge created an infrastructure of science and courage that echoes to this day. It was the ultimate test flight. And the men who flew it were not just pilots. They were navigators on an ocean that had never been charted, sailing on a ship that had never been tested, toward a shore that had never been touched. They were going to a place where a single miscalculation, an error of a few seconds in an engine burn, could mean being stranded in orbit around the moon, or missing it entirely, destined to drift forever in a sterile, sunlit grave between worlds. The pressure was astronomical, the risk absolute, but they went. And when they arrived, they found a world of profound, terrifying beauty, a world of silence, a world where the sky is black, even at noon, and the earth hangs in the darkness, a beautiful, lonely blue and white jewel. This is the story of how we reached the farthest shore we have ever known. It is the story of the first and, so far, the only time that living beings have set foot on another world, main body. The vehicle for this audacious journey was the Saturn V rocket. To this day, it remains the most powerful machine ever built by human hands. It stood taller than a 30-story building, a gleaming white tower of fuel and ambition. Its first-stage engines produced a thrust equivalent to 32 Boeing 747 jets at full power. The sound of its launch was not just loud. It was a physical force. People felt it miles away, a deep, rumbling vibration in their chests. The ground itself shook. At the very top of this colossal stack sat the Apollo spacecraft, a delicate-looking assembly of 3 modules. The command module, the conical home for the 3 astronauts during most of the journey. The service module, a cylindrical section holding the main engine, power, and life support. And tucked inside a protective shroud, the lunar module, a spidery, fragile-looking craft with foil-wrapped walls and spindly legs. It was a lander. It looked like something a child might build from spare parts, but it was engineered to perfection. It was the only part of the ship that would go down to the lunar surface. Its job was to take 2 men down and then, miraculously, lift them back off again. The journey began, as all journeys to orbit do, with a violent, earth-shaking ascent. For the astronauts strapped into their couches at the tip of this controlled explosion, the experience was overwhelming. The G-forces built and built, pressing them into their seats. The vibration was so intense it made it hard to read the instruments. Then, one by one, the stages burned out and were jettisoned. The first stage fell away, then the second. Finally, the third stage engine fired to push them out of Earth orbit and onto a path to the moon. This maneuver was called translunar injection. It was a burn of such precision that getting it wrong by even a small margin would have dire consequences. And then the engines cut off. The noise vanished. They were coasting. For 3 days they fell toward the moon. Inside the command module, life took on a strange, quiet routine. They were in microgravity, so everything floated. They ate rehydrated food, exercised as best they could, and navigated. But outside their windows, the view was transforming. The Earth, which had filled their view at launch, began to shrink. It became a sphere, then a brilliant crescent, and then gradually just a disk. A beautiful, swirling blue and white marble hanging in the blackness. It no longer looked like a world, a place. It looked like an object, a precious, fragile-looking object. The moon, which had started as a faint gray coin in the distance, grew steadily larger. It didn't look like the friendly, romantic moon of poetry. It looked dead, a battered, cratered, ancient landscape. It had no air, no water, no life. It was a desert of rock and dust illuminated by the harsh, unfiltered light of the sun. The most profound moment of the outbound journey came not from the first mission to land, but from the first to orbit the moon. Apollo 8 at Christmas, 1968. Their mission was to test the command module in lunar orbit, to scout landing sites, and to pave the way. As they emerged from behind the moon on their 4th orbit, the crew witnessed something no human eyes had ever seen. The Earth rising over the barren, gray lunar horizon. Bill Anders, one of the astronauts, scrambled for a camera with color film. The photograph he took, Earthrise, became one of the most influential images in history. It showed our world, not as a map, not as a collection of countries, but as a single, isolated, beautiful oasis in a vast, empty blackness. It was small and it looked terribly alone. That image is credited with helping to launch the modern environmental movement. It gave us a new perspective on our home. We saw it for the first time as it truly is, the only home we have. But for the landing missions, the real test was still to come. After entering orbit around the moon, 2 of the astronauts would float through a tunnel from the command module into the lunar module, nicknamed the LEM. They would then separate from the mothership. The 3rd astronaut would remain alone in orbit, a solitary sentinel circling the gray world below, waiting for his companions to return. The descent of the LEM was the most tense, white-knuckle part of the entire mission. It was a machine that could only fly in the vacuum of space. It would be useless on Earth. Its engine had to work perfectly. It had to slow the craft down from orbital velocity to a gentle hover. The astronauts, standing up in the cramped cabin, guided it down manually using a combination of computer guidance and their own eyes. For Apollo 11, the first landing, the chosen site, turned out to be far rougher than expected, littered with boulders and craters. Neil Armstrong, the commander, saw the computer was taking them into a dangerous field, with fuel running dangerously low, alarms sounding in the cabin, and mission control on Earth holding its breath. He took manual control. He flew the LEM like a helicopter, skimming over the boulder field, searching for a safe spot. He had about 30 seconds of fuel left when he finally found one. "Contact light," called out Buzz Aldrin, as a sensor on one of the legs touched the surface. A few seconds later, Armstrong spoke the words that echoed around the world. "Houston, Tranquility Base here. The Eagle has landed." The relief in mission control was palpable. They were down. They were on the moon. After the checks were done, after they suited up and repressurized the cabin, Armstrong opened the hatch and began to back down the ladder. A black and white camera on the side of the LEM broadcast his movements to over 600 million people on Earth. And then he stepped off the footpad. "That's one small step for man," he said. The static slightly garbling his transmission, "one giant leap for mankind." Tonight we will explore that silence. The silence that followed the roaring engines of the Saturn V. The silence that fell after the last astronaut climbed the ladder of the lunar module and left the moon to its ancient solitude. This is not a story of adventure, but of aftermath. It is the story of the long pause. We will descend from the pinnacle of Apollo into the quiet, complicated decades that followed. This is a chapter about budgets and shifting priorities, about technological plateaus and the slow, unglamorous work of building endurance. It's about why the edge of human travel has remained for half a century, right where we left it in 1972. So, let's return from the moon. Let's come back to Earth. Not in a triumphant splashdown, but in a gradual settling. Let's understand what happens when a species looks at the next horizon, calculates the cost, and decides, for a while, to catch its breath. Hook. Imagine a graph of human distance from Earth. For all of history, it's a flat line, hugging the ground. Then, in the 1960s, it becomes a sheer, vertical cliff, rocketing upward until it touches the moon. And then, just as suddenly, it plateaus. It becomes a long, flat, unbroken line that stretches for decades, right up to the present day. That flat line is the long pause. It is one of the most peculiar and defining features of the space age. We proved we could perform miracles. We developed the machines, trained the people, and possessed the knowledge to go back to the moon, and even beyond, to Mars. The blueprints were drawn. The missions were planned. Wernher von Braun himself had detailed plans for a massive mission to Mars using nuclear-powered rockets, envisioned for the 1980s. It was all possible. And then it wasn't. The long pause wasn't declared or decided. It wasn't a single event. It was a slow fading, a cooling of ambition, a reordering of national needs. The world that had driven Apollo forward, a world defined by the binary, existential struggle of the Cold War, was changing. The political fuel that powered those massive rockets was running out. But to see the pause as merely a failure of will is to misunderstand it. It was also a period of necessary learning. We had sprinted to the moon, but we were gasping for air, and our technology was built for sprints, not marathons. The long pause was when we learned to breathe, when we traded the poetry of departure for the prose of maintenance, when we stopped asking, "Can we get there?" and started asking, "Can we stay alive long enough to make it worthwhile?" The space stations, the shuttles, the international partnerships, these were the products of the pause. They were not as glamorous as a moonwalk, but they were the foundational work for any future that lies beyond. The long pause was not an empty silence. It was a silence filled with the quiet, patient hum of a species learning to walk before it could run again. We are going to explore the anatomy of this stillness. We will look at the political realities, the technological hurdles, and the profound psychological shift that turned our gaze from the depths of space to the fragile surface of our own planet. The long pause is the gap between what we achieved and what we maintain. It is the space between the dream and the reality. And to understand how far we can travel next, we must first understand why we stopped. Main body. The end of the Apollo program felt to many like an abrupt and premature conclusion. The last mission, Apollo 17, splashed down in December 1972. The infrastructure was still in place. The teams were still sharp. The public, while its attention had waned, still held the moon landings as a point of immense pride. Yet, the political constellation that had made it all possible had shifted irrevocably. The Cold War was still ongoing, but its nature was changing. The doctrine of mutually assured destruction had created a grim, stable standoff. The symbolic victory of planting an American flag on the moon had been won. There was no longer the same urgent national survival imperative to outdo the Soviets in space spectaculars. At the same time, the United States was being torn apart by internal strife. The Vietnam War was a bloody, costly, and deeply divisive quagmire. The civil rights movement was demanding justice and equality. Cities were facing economic decline and social unrest. The environmental movement was gathering force, sparked in part by that very Earthrise photo from Apollo 8, which showed a planet that looked small, fragile, and in need of care. In this context, the cost of Apollo became politically unsustainable. At its peak, NASA's budget consumed almost 4.5% of the entire federal budget. To sustain a program of lunar bases and Mars missions would have required maintaining or even increasing that level of investment. Congress and the public looked at the problems on Earth, poverty, war, pollution, and asked a simple, powerful question. Why are we spending all this money on rocks when there are people suffering here? It was a question that space advocates have struggled to answer convincingly for decades. The purely scientific returns, while profound, were abstract to most people. The technological spin-offs, from CAT scanners to freeze-dried food, were real but seemed a convoluted way to invent new technology. The existential argument that humanity must become a multi-planet species to survive in the long term felt like a science fiction concern compared to the pressing crises of the day. So, the funding was cut. The Apollo 18, 19, and 20 missions were canceled. The Saturn V assembly lines were shut down. The giant crawler transporters were put into storage. The brilliant minds of the Apollo era dispersed to other projects, other industries. The mighty vehicle assembly building at Kennedy Space Center, built for the Saturn V, fell silent. The first phase of the long pause was, therefore, a political and economic retreat. The age of epic government-led exploration seemed to be over. The question was, what would come next? The answer was a fundamental shift in strategy. If we weren't going to go farther, we would learn to stay longer. The goal moved from distance to duration. This new era was defined by two major programs, the Space Shuttle and the first space stations. The Space Shuttle was sold as a new, practical and cost-effective way to access space. It was reusable. It would fly like a plane. It would make spaceflight routine and affordable, launching satellites, conducting research, and building a space station. It was a vehicle for the long haul, not for the grand leap, and in many ways it was a marvel. The shuttle was a flying truck, a laboratory, and a repair platform all in one. It gave us the Hubble Space Telescope, not just by launching it, but by repeatedly servicing it, saving it from blindness, and upgrading its instruments over 5 separate missions. It built the International Space Station piece by painstaking piece. It carried astronauts from dozens of nations, internationalizing spaceflight in a way Apollo never did, but the shuttle also kept us confined. It was never designed to go beyond low Earth orbit. It couldn't even reach the moon. Its operational ceiling was about 600 kilometers, a fraction of the distance we had already traveled. It was a magnificent machine, but it was a commuter bus that only ran to the suburbs. It turned the act of leaving Earth into something that felt, from the outside, almost routine. And in doing so, it inadvertently reinforced the public perception that space was no longer a frontier, but a workplace. The other pillar of the pause was the space station. First with Skylab, then with Mir, and finally with the International Space Station, we began the critical work of learning how the human body and mind cope with long-term exposure to space. The Apollo missions had been short, frantic trips. We knew little about what would happen to a human after 6 months, a year, or more in microgravity. The stations taught us the harsh realities we discussed in Chapter 3. The relentless loss of bone and muscle, the fluid shifts, the potential vision problems, the psychological toll of confinement and isolation. This wasn't glamorous work, but it was absolutely essential. A mission to Mars would take at least 6 months one way. Without the knowledge gained from the long pause aboard space stations, such a journey would be a death sentence. This points to the second crucial reason for the pause: technology. The Apollo spacecraft were magnificent, but they were designed for one purpose: to get to the moon and back in less than 2 weeks. They were not built for long-term endurance. Their life support systems were open loop. They carried all their oxygen and water and dumped their waste overboard. To go to Mars, we would need closed-loop systems that recycle air and water with near-perfect efficiency. We would need much more powerful and efficient propulsion to shorten the travel time and reduce the crew's exposure to radiation and weightlessness. We would need robust radiation shielding, advanced medical facilities, and power systems that could last for years. In the 1970s, and for a long time after, we simply did not have that technology. The long pause became a necessary period of research and development. While the human spaceflight program seemed to stall in orbit, the fields of material science, computing, robotics, and medicine were advancing at a breathtaking pace, often driven by other industries. The smartphones in our pockets today have orders of magnitude more computing power than the Apollo guidance computers. These advances would be critical for any future deep space vehicle. There was also a third, more subtle dimension to the pause: a cultural and psychological shift. After the euphoria of Apollo, a kind of disillusionment set in. The moon hadn't transformed life on Earth. It hadn't ended war or poverty. For a generation that had witnessed such a profound achievement, the return to earthly problems felt like a letdown. The grand narrative of exploration gave way to a more fragmented, complex view of the world. The future, which had once seemed to be waiting in the stars, now seemed to be a problem to be solved here at home. This wasn't all negative. This inward turn led to a greater focus on understanding and protecting our own planet. The environmental movement, the growth of computing, the biotech revolution, these were the beneficiaries of the post-Apollo intellectual and financial capital. Yet, the dream of exploration didn't die. It was kept alive faintly by the one part of the space program that was pushing relentlessly outward: robotic exploration. While humans stayed in orbit, our robotic proxies became the true pioneers. The Viking landers touched down on Mars in 1976. The Voyager probes toured the outer planets and then headed for interstellar space. Later, the Mars rovers, Sojourner, Spirit, Opportunity, Curiosity, Perseverance, would turn the red planet from a distant point of light into a familiar, explored landscape. These missions were cheaper, less risky, and often returned more pure science than a human crew could. They became the vanguard, extending our senses and our presence across the solar system, even as our bodies remained behind. The long pause, then, was not a single thing. It was a complex interplay of art politics, the end of the Cold War imperative, and the reprioritization of domestic spending. Economics, the immense, recurring cost of human spaceflight, and the search for a cheaper, more sustainable model. Technology, the necessary gap between the ability to reach a destination and the ability to survive the journey there and back. Culture, a shift in public mood from expansive optimism to pragmatic problem-solving. For 50 years, the farthest footprints have remained on the moon, untouched. They are a monument to what we once did. But the space stations and shuttles of the long pause are a different kind of monument. They are the workshops where we have been slowly, patiently, building the tools for the next journey. We stopped not because we failed, but because the sprint was over. The next phase required a different kind of strength, the strength of the marathon runner. It required the patience to learn, to adapt, and to build a foundation that could support a future not of flags and footprints, but of homes and habitats. The long pause has been a time of gathering strength, a time of learning the delicate art of living in space, a time of letting our robots scout the path ahead. The silence after Apollo was not the silence of an ending. It was the quiet concentration of a climber, resting at a base camp, studying the map for the next, even more difficult ascent. The sound of the space shuttle's engines was different from the Saturn V's. It was still a roar, but it was a more familiar one, a sound that over 135 missions became part of the background noise of the late 20th century. It was the sound of routine, and in its own way, that was as miraculous as the thunder of Apollo. We had made the extraordinary ordinary, but in making it ordinary, we lost something. We lost the sense of boundless possibility. The edge of the map, which had been pushed all the way to the moon, receded back to low Earth orbit. The shuttle was a magnificent machine, but it was a caretaker of the near frontier, not a ship for the far one. The long pause has been a time of immense, if quiet, progress. We have learned how to build and maintain a permanent human presence off-world. We have created a model of international cooperation in space. We have developed technologies of recycling and life support that will be the bedrock of any interplanetary vessel. We have used our robotic avatars to explore every planet in the solar system and beyond. The footprints on the moon have waited. They have been patient, and now the silence is beginning to break. New rockets, more powerful than any since the Saturn V, are being tested. New plans for the moon, under the Artemis program, are being drawn, not for flags and footprints, but for sustainable presence. The goal is no longer just to visit, but to learn how to use the resources of another world, to mine water ice for air and rocket fuel, to build habitats from lunar soil. The long pause is not over, but it is ending. It is giving way to a new era, one that seeks to blend